Hi, U10s. This is our final topic for the year before, of course, we have exams and revision. This is financial maths, and just to give you sort of an overview, financial maths is a topic in general maths. And so this, if you're going on to do general, it's a good topic to do and to give you some exposure to some of these. And we're going to start with exponential growth and decay. So you can have exponential growth, which is increase. We can have decrease. And we can, of course, apply that to, in particular, financial maths, but we can really apply it to anything, such as like population growth or population decay. So let's get started. Now, first of all, some of these things we need to know. Well, if something's growing, then let's just say, for example, if I was to have this guy over here, well, the growth rate sort of will be, let's say it was growing at 10%. Then here, my rate would be 10, so 10%. And if I was to put my percentage in this, then 10%, well, what is 10%? My growth rate would be, well, 1. It's got to clearly be greater than 1. And let's put in 10 over here, 10 over 100. And of course, 10 over 100 is the same as 0.1. If I add that, so 1.1 is, so a number greater than 1 is what we would call growth. And likewise, we could have, if something was declining at 10%, then we could have 1 minus, if I had 10 over 100, that's 0.1, that's going to be 0.9. Now, of course, this over here is what we call decay. All right, so for example, we're trying to flatten the curve at the moment and, beat this pandemic. The reason why I was getting out of control is because this growth factor was just it was too high. People are passing it on to other people. And if they're passing it on to more than one person, then we're in this sort of rate of growth here, which we don't want. Okay, in this case anyway. Certainly if you were looking at money, if you're investing in money, you want it to grow. And the power of exponential growth is really quite interesting. So we're going to look at some growth rules. Okay, so we're going to look at some growth rules, and we're also going to give some rules for various situations. Let's get started into some of these. First of all, I'm going to sort of make note that this is the formula that we're using for exponential growth. And once we look into compound interest, this is going to be the formula we need, where A naught is sort of the initial value, if you like, okay, which is going to increase or decrease, hopefully increase if we're talking about money. Okay, so this is the initial value here. R is what we call the rate. So R is like our interest rate, if you like, or rate of growth, and that's going to be sort of as a percentage usually. And of course, N is sort of like the number of it could be like the number of years. Usually this sort of refers to some form of time, whether it be, usually it might be sort of per annum, so it could be the number of years. All right, so let's try and get some of these and do an exponential rule for this. John has a painting that is valued at $100,000. So let's write out this. So A naught is equal to 100,000. And it says it's expected to increase. So increase means that we've got to go ahead and find our growth rate by 14% per annum. So per annum means per year. Now, let's go ahead and find what our growth rate is. So we start off with, up here, 1 plus R over 100. And of course, R is 14%, but it's just 14. This is sort of in percent here. Let's go ahead and throw the 14 in here. So if I get 1 plus 14 over 100, well, as a decimal, if I was to get dividing by 100, so let's get the 14 and let's divide that by 1, 2. As you can see, 0.14, which means that if I add those together as a decimal is 1.14. Now that I've come up with all of that, what we can go ahead and do is we can now turn this into an exponential equation. Similar to this thing over here. So the time, at any time, the amount this painting is worth is, let's throw in what we know. Well, it's going to be A naught times, well, let's put in here, this is our sort of our growth rate, or it could be declining, but it's our growth rate. So we want to put in 1 plus R over 100, and then to the power of N. That's what we want. Now let's throw it. Now, of course, we've already worked out what our growth rate is. That's 1.14. So we can go ahead and put that in. We also know that the initial value of this painting is 100,000. So let's go ahead and put that in, 100,000. Let's put in 1.14. And of course, we want to know what it's worth after n years. So that's just going to be to the power of n. All right, so for example, if I was to go ahead and throw this into the calculator, let's go ahead and do that. You can see here, if I go ahead and put in 100,000, 1, 2, 3, and let's just say we wanted to work out how, let's put in 1.14. Let's say after 1 year, well, you would expect 14%, 1 year, 14% of 100,000. You would expect that to be 114,000, which it is. Now, if I go ahead and press up here, this is the cool thing about these calculators. Let's say I want to use that again. If I press enter, it actually copies it down there. So you don't have to write it all again. You can also use control paste as well, control copy. So if I go control C, it actually will work as well. Let's have a look. Let's delete that and let's press control V. Get used to some of these things because it makes your life a lot easier. Okay. Now, let's say, but see, interesting, yeah, sure, we could work it out after 1 year pretty comfortably, but what happens if we're looking after 10 years? Let's have a look. This is the sort of the power of compound growth. As those years go on, after 10 years, this painting would be worth $370,722, and it started off at 100,000. So in just 10 years. Now, look, if the stock market would probably average around about 8, 9, 10% per annum. So you can see there that investing and compound investing is a really powerful thing. We're talking about in 10 years, you've got 3.7 times, almost 4 times your initial investment in this case. All right. So, and well, you know, if you invest in superannuation and things, let's start looking now. Let's change this rate to something a little bit more. Let's change it to 9%. If you to get 9% per annum, let's see how much your $100,000 would be in 30 years. Yep, that's 1.33 million pretty much. So as you can see, if you had $100,000 and you increased it by 9% using compound growth, you're going to have $1.33 million in 30 years. All right, so the power of compound interest is really, really quite important, very important to understand compound growth. Probably one of the most, real life, importance all year, this stuff, absolutely. Now, let's have a look here at a city's initial population of 50,000. Now, this time it's decreasing, okay? We're not always going to be looking at money. In this case, population, well, we can increase, it can decrease. So, first of all, let's start off. Here's A naught. This is our population to start off with. That's 50,000. Step 2, let's work out what our rate is. Now, of course, we know that 1 is the same, stays the same. We're looking at, if I'm looking at greater than, if I'm looking at greater than 1, we're looking at growth. So we should expect, if this is sort of going down, we'll call it decay, and that would be if our growth factor is less than 1. So let's go ahead and work out that. Now, so decreasing this time, our growth rate or growth decay is, it's 1, but it's not plus. We're minusing because it's a 12% per year reduction. Okay, so that's what we want. Now, if I go ahead and find out what my growth rate is, well, 12 divided by 100. So that's going to be 12. If I'm dividing by 100, 2 decimal places, we've got to subtract 0.12 from 1, which of course is 0.88. We want to come up with a decimal answer. We know that it's going to be less than 1. Let's do that now, and let's put it all together. So the amount at any year is, let's put in our initial amount. We always need that initial amount. And then, of course, if we get our growth rate or decay rate, this time it's 0.88, and to the power of n years. Okay, so let's have a look at something like this. Well, clearly we know that after 1 year, you would expect like a 12% decrease. Let's go ahead and find out what that's going to be. 50,000, and let's multiply that by 0.88, and then let's do that after 1 year. Okay, so we've got a 12% decrease in 1 year. So that's actually, as it turns out, we're looking at, it's going to be 44,000 people after 1 year. What about though if I'm looking after, if I'm going to something like, let's say do 5 years? Okay, that's going to be to the power of 5, and it's almost halved in 5 years. All right, so once again, that compounding going the other way. All right, at the moment we're talking about a virus which it can actually go down pretty quick if that growth factor is under 1. All right, so it can go down really quite fast. So as you can see, it's almost halved in 5 years with a rate, a compounding rate of 12% decay going down. All right, now let's have a look, and now that I've got those, can I get you to pause, try this? I would like you to pause now, have a go, and I'm going to reveal my answer shortly. So if you want to have a go at this to see if you test your understanding, have a go and pause it now, please. Okay, so you can see that when doing these, I've just done some underlines. So what we're going to need is we're going to need the initial amounts or initial population in the second one. We're going to also need if it's increasing or decreasing, because so we can work out the growth or the decay rate. And we've also got this rate. And generally speaking, you're looking at a percentage, because now we can go ahead and write out what we know, which we can hopefully do here. Write out our initial value or population for the second one. Write out what our rate is. Now, and of course, we then have to work out what our growth rate is for the first one. So it's 1 plus 16 over 100 is 0.16 is a decimal. Let's add that to 1, which is 1.16. We want to see it growing, so this number has to be greater than 1. Otherwise, it's not growing at all. That's a big telltale sign if you've got the right answer there. And from there, we can then throw that into our equation, like so, where n is the number of years. And usually it is years, but sometimes it could be months and things when we get into some other questions later, looking at financial. All right, and likewise, we've got a 10,000 population to start with, but this time, look, it's decreasing by 9%. So we've got to work out what our decay rate is. So instead of adding 9 over 100, we're subtracting 9 over 100. Now, 9 over 100 is decimals, 0.09. We can go back 2 decimal places, 1, 2, and if I subtract 0.09 from 1, it gives me 0.91. That's decay. It's going to get less and less. So therefore, the exponential equation is going to be this, where n is the number of years. Okay, so I'm hoping that's making a little bit of sense now. Now, let's have a look at doing some of these. I'm going to be looking at another example, and let's see if we can do, sort of a more worded sort of problem. All right, now it says house prices are rising at 9%. So the first step is we want to get our highlighter or whatever, and let's underline the information that we need. So 9%, and it's rising. We need that bit of information. And also our initial value is 600,000. Now it says determine a rule for the value of Zoe's flat in n years' time. So let's go ahead and we're going to say that our rule is V, that's the amount at any time, and we need to, well, let's write out what we know. Well, first of all, R is equal to 9%. That's nice, it's in percent, that's good. The initial value is equal to 600,000. Okay, 600,000, and we're looking in, and N is sort of the years. Okay, so N is years, and it's compounded yearly. All right, so now let's go ahead and work out what our growth rate is. So our growth rate is, well, it's 1. Is it rising? Yes, so we've used plus 9 over 100. Let's put that in, 9 over 100. Well, that's the same as 1.09. And now that we've done all the hard work, that's, I think, the hardest thing for a lot of students to get is that sort of growth rate. Now, let's go ahead and put that in. It's going to the value at any time is 600,000, the initial value, times our growth rate to the power of how many years, which is, of course, just n. Now, we can use this rule for finding number things. For example, what will be the value of a flat next year? So, when n is equal to, once you've had one compound when it comes to this of 9%, so when n is equal to 1, we can just go ahead and sub it into the equation. So, 600,000. Let's go ahead and put that in. 1.09 to the power of 1. Now, this thing actually sort of shows you, this sort of is the growth. It's growing at 9%. So it does, by getting this formula, it's doing all the hard work for you. Now, of course, I'll need to work that out. 10%, 60,000. So I'm guessing it's going to grow 54,000. So I'm hoping this is going to be 654,000. But we've got a calculator, so let's do that. Let's practice. We've got 600,000, and let's go ahead and 1.09 to the power of 1. And that's going to give us, no, we want to the power of 1. There you go, 654,000. Okay, so for next year, what would be the value of a flat next year? So after 1 year, it's going to be valued at $654,000. In 3 years' time, we're just going to substitute it in. Well, it's going to be a bit harder to work. Now, think about it. After that, your new investment is then $654,000 after 1 year. Then we're looking at a 9% increase on that. That's what we're talking about, compound interest. You're compounding, it's growing, and you also that rate stays the same, and it's compounding per year. So we're looking at 9% on this in our second year, and then so on and so forth. But the magical thing about this is that we don't have to do like a series of calculations. We can just go ahead and throw it into this formula, this exponential formula here. So after 3 years, let's go ahead. Let's press enter, that'll paste that down. Let's go ahead and delete that, and let's go change that to a 3. And as you can see there, we've got 777, and we're looking at dollars. Let's just round it down. 777 and 17. So after 3 years, we're going to say that this thing is worth 777,000 and what was it, $17. All right. Now it says use trial and error to find Zoe's flat. What will be valued at? Now, of course, trial and error. We can throw in different numbers. Now we know that after 3 years, the flat's going to be worth 777,000. So what we could do is, well, let's work out what after 4 years, after 5 years, and see if I get it higher. I'm going to show you a bit of so let's try that. Let's go now. I've got up here. We want to work out where it's 900,000. So let's try this after 4 years. Now we're getting closer. Let's press enter, and then let's change that to the power of 5. Okay, that's worth more than 900,000. So I guess a bit of trial and error, we can say, okay, well, it's somewhere between 4 and 5. It's going to be less than 5, and it's going to be more than 4. It's probably going to be closer to 5, I would have thought. So let's try, I don't know, let's try 4.75. Let's give that a go. 4 3/4 of a year. Okay, we're getting there. And then as you can see, we can get closer and closer. That's how we would do trial and error. Now, I can show you a way, the power of these calculators is that we can go ahead and solve and find the exact answer. Well, let's try 4.71. All right, we're getting closer. I'm within $388. Technically, let's go, okay, let's try to the power of, let's do to the power of 4.70. All right, so somewhere between 4.7 and 4.71 would be our answer. Okay, so let's give this. So we've basically worked out that using trial and error, that it's sort of somewhere between 4.70 and 4.71 years. Now, here's a cool thing. Let me show you how to do on the calculator. Now, I've actually got it here. This is sort of what you would need to do in your calculator. So we're going to use the solve function. I'm going to show you how to use this. Now, first of all, really important you can get into the habit of using your CAS is that we want to press the menu button. Then we want to, here's a shortcut. If I press menu 3 and then 1, that is going to be my shortcut to solve. Okay, now this, of course, I might ask a question in the exam for this because we want to see some evidence that you can use your CAS calculator. Okay, so now if I go ahead and throw this in, and I go ahead and I want to find where the value is 900,000. I then sub it into the equation, but this time I'm going to tell your calculator at the end that we've got to do comma n. Okay, and comma n means that we're solving for n. We want to find the number of years. Now, let's go ahead and show you in the CAS calculator. So, here we go. Here's the CAS. And so, let's go show you where to solve. First of all, we'll go to menu, and then we go algebra. You can see there's a little 3 there. So, menu 3, you're going to need this for methods and general maths as well if you go into general maths. So, it doesn't matter which one. Menu 3 and then 1. Okay, so let's go ahead now solving. Now, as you can see, we were trialing different values of n. So I'm going to get this, and by pressing enter, let's see what it does. Isn't that amazing? That actually copies it down into those brackets there. Now, of course, we don't want to. We plugged in our little value, and we got pretty close. But let's go ahead and change that to the power of, let's put an n in there. Now, you could put in x and stuff, but the question's in terms of n. So now, if I press enter, let's see what happens. Not going to work because you've got to tell your calculator that what you're solving for. So that's going to be, you need to put a comma in there, which is this thing here, and then press N. That's still not working. Now, why is that not working? First argument of solve. Oh, we don't have an equal sign. That was silly of me. Let's press enter in here. So I've actually got to solve. This time we know that the value, it gets to 900,000. So you can't solve without an equal sign. 900, 1, 2, 3, 900,000. Let's see if that works. Press enter. It did. Okay, so these are the sort of, I did those mistakes on purpose because I want to show you that's what's going to happen when you try this for the first time. If you don't have an equal sign, you can't solve an equation because an equation has an equal sign. And likewise, if we don't tell the calculator that what we're solving for, in that way, we're using a comma, we're also going to get some errors. So there you go. You can see there that there's no need for trial and error. Why would you do trial and error when your calculator can work it out for you? So there you go, 4.7, let's do the 3 decimal places, 70. Well, let's round that 4 up to a 5. because that's a 9. 4.705 years. So let's go ahead and write that down. So technically, using our calculator, we can say that to 3 decimal places, the time was approximately equal to 4.705 years. Let's say that's to 3 decimal places. Okay, now you need to practice with your calculator. The scientific calculator, yes, will work with some things. You certainly can't do this stuff with your scientific calculator. So I'm going to urge you to be pleased using your CAS calculator when doing these questions. Get in the habit of these. We've got to practice these. These are the questions you'll be doing in your work lesson. I'm pretty confident there's not too many there. You should be able to get those done in your work lesson, no problem. All right, that's it for me. Good luck, and I'll see you in class.